Yeah, so thank you for coming, and I would like to also to say so the topic of this trimester is stochastic dynamics of non-equilibrium systems, and which is quite remote from this topic what I would like to explain in next 3 lectures about synchronization. In fact, so in my opinion, so when one speaks of non-equilibrium systems, one somehow has in mind that there are also equilibrium systems, and non-equilibrium is something which is maybe not so much different from equilibrium, so nearly equilibrium or quasi-equilibrium, or at least you use something from equilibrium systems, and which is in realm, say, of thermodynamics and classical statistical physics. Now here, in the theory of synchronization, one starts from, I would say, extremely non-equilibrium systems, so that they are even not, in many cases, not even close to what is described in usual statistical physics. And so it is extremely dissipative systems which serves as some maybe generators or whatever. So it's even very far from the realm of usual statistical physics and its modifications. And nevertheless, so there are some aspects where what is done in this field may be somehow linked to the, say, classical equilibrium or, say, weakly non-equilibrium situations. And in many cases, it's just synchronization is some kind of buzzword which is used maybe also in fields which are probably some other macroscopic or collective phenomena should be used. Okay, anyhow, I will start with very simple situation, elementary dynamical, and at the end of this lecture it will be also stochastic and chaotic. And maybe in next lectures today and on Friday, I will describe more complex situations, and especially so-called many-body systems, where indeed methods similar to methods of statistical physics are used. Okay, so my plan is that in this lecture, so that I will introduce this notion which are in the center of the theory of synchronization as self-sustained oscillators. And then there will be some ways of mathematical description of these oscillators, and which allows to introduce phenomenon of synchronization. And then I will speak on the ways how physicists try to generalize this notion to noisy and chaotic oscillators. And I would say so that this is a part of well-established modern theory of dynamical, smooth dynamical systems, while here, say, many problems are solved maybe on physical level, so, but I don't think so that there exists a really well-established mathematical theory. And in the course, so the many things will be simple, but nevertheless, please ask me at any point when something is not clear, because it's indeed what I will try to explain comes from somehow a little bit different community, maybe compared to what is in the focus of this program. So let us start with self-sustained oscillators. Now, the idea is so that there is some oscillating object which is active. So there is some supply of energy to it. And this is typical when you construct such oscillating system and you want it to oscillate without dissipation so that oscillations don't disappear. So you have to supply energy, and this is done in modern clocks in form of battery and generator, electronic generator operates, but in previous time it was, say, weight, which had large potential energy, and this potential energy was supply of energy to the clocks. And in the, so what we need is that the steady state equilibrium in such a system is unstable, which means so that this parameter, which is typically for dissipative system, will be negative, gamma, but here it is positive, and it means so that small perturbation of equilibrium, they grow, but they grow also in an oscillating manner with some characteristic frequency in such linear systems. And from the physical viewpoint, it is clear that this energy growth cannot continue to infinity because there are some saturating mechanisms, and they are nonlinear terms which appear in such elementary equations in this form and, or in a more symmetric form like here. So energy grows if the amplitude is small, but it decreases if amplitude is large. And so somewhere in between, there is some stationary amplitude of oscillations. And this, mathematically speaking, is a limit cycle in this system of differential equations. Here, there's a second-order differential equation. Z is complex variable. And here it is a famous van der Pol equation. And this is called, in different contexts, Poincare oscillator or Hopf normal form or Stewart-Landau oscillator. Okay, so in both this situation, there is a stationary oscillating, periodic in time oscillating solution. So also in different contexts, in physics, one calls the self-sustained oscillator. Sometimes it is called autonomous oscillator because there is no any periodic forcing driving it. Or in biology, it is quite often is called endogenous rhythm because so it means so that this is rhythm not imposed from outside, but produced by the living organism itself. Okay, so this is the basic object. So there are different types for these oscillations, so which in principle are all the same, but still you distinguish several how it properties are maybe particular properties could be different. So one often distinguishes self-sustained oscillations which are quasi-harmonic. So it means so that it's a nearly sine function or looks like some kind of oscillation, looks really like a smooth function of time. But there are many cases where the oscillations looks like a series of peaks or maybe some series of jumps. These are examples of so-called relaxation oscillators. So that also it's typical for many systems, especially in biology. So this is a typical form of how a neuron is firing. It is firing as a real narrow spikes. And its neuron in the brain is exactly a self-sustained oscillator. in many cases of this type. Okay. Okay, so now I'll give some just elementary examples of where the systems appear. So you know that if one has a microphone, here we don't have loudspeaker. It's just for recording my voice, this microphone. But if we had loudspeaker and I will come close to it, there could come a whistle, which is due to this feedback loop. So there is some amplification here, which brings energy to the system, and there is oscillating system due to, for example, resonance frequency of this loudspeaker or microphone, and it all becomes oscillating object. So if you take microphone out of the speaker or decrease amplification, so it will be below threshold and there will be no self-sustained oscillations. So classical clocks, pendulum or electronic are also of this type. So here energy comes from spring or from battery or from the weight. Also very elementary examples, so which you can use as a demonstration in the lecture, is a metronome where so this pendulum oscillates, say maybe for half an hour, nearly periodically due to energy, release of the energy here in the spring. In physics, there are many. Laser is example of such a self-sustained oscillator nowadays. So there are very funny objects in so-called spintronics, which also are self-sustained oscillators. So subject of some hope to have a next generation of electronic devices based on such tiny magnets in matter which oscillate due to imposed current, spin carrying current with a constant amplitude. Yes. Okay, so one of the popularity of this field of synchronization is in the fact that such objects are not restricted, say, to physics and maybe to some exact sciences like chemistry, but their concept can be applied to many objects where you even don't have equations and you don't know how to exactly describe them, but nevertheless, you observe a periodicity there. And this periodicity is not due to external some periodic forcing, but it is intrinsic. And probably the most striking example is this firing neuron. Yeah, so which is, okay, so here still one can fairly well understand how this rhythm is generated, because equations for a neuron are basically physical equations for currents and voltages. But there are more complex situations. For example, so-called circadian rhythm in the organism, which is nearly 24 hours internal periodicity of sleep and wake periods, which is not due to illumination, but just intrinsic. And there are some processes in cells which give such a periodicity. And you don't have equations, but nevertheless you observe it. And you know that this is self-generating periodic activity. So it belongs to this class. And therefore, you can apply the concepts which are developed for situations where you can describe everything with equations also to situations where you don't have equations, but you observe similar phenomena. And I will give some examples also of this. Okay, so just summarizing what was in this introduction, there are special objects which mostly adequately are described from the viewpoint of dynamical theory, or in mathematics it's essentially a theory of nonlinear differential equations. And the property is that these are autonomous systems of nonlinear differential equations can generate periodic oscillators. In this theory, so there is a notion of limit cycle, which is a periodic trajectory, which is stable, and it represents these periodic oscillators. They exist without periodic forces. So these are, so you don't maybe learn such things in elementary theory of ordinary differential equations, and in physics, when you speak about linear oscillators, you also don't have this, but probably I introduced it quite well. Is there no questions? We proceed. So how we now use these properties to understand phenomenon of synchronization? Now, the main idea in the description is in the following, that this is the limit cycle which I spoke about in the some phase space of a differential equation. Phase space is the space of all variables. And there is a periodic trajectory, so which represents periodic, stable periodic oscillations, and all other trajectories come close to it. And so if you look on something which can be called amplitude, or maybe amplitude in quotation mark, which is a variable which describes the size of oscillations, you see so that it is fixed, and the only variable which changes on this limit cycle is the phase. And phase rotates. You can always normalize it in such a way that it rotates with a constant velocity, which is exactly the frequency of the oscillations. Yeah? So after time 2 pi over omega naught, you return back, and this means so that this is the period of the oscillations. Yeah? And the amplitude, you see, because it is a stable limit cycle, we said that amplitude grows if it is small and decreases if it is large. It is exactly equilibrium amplitude. So it has such type of relaxation. And if you look on this situation from the viewpoint of notions of stability, you can realize that the amplitude is stable because any perturbation in the amplitude returns back. But the phase has no real stability property. If you look on this equation, and you shift phase by some any amount, this perturbation neither grows nor decays, so it remains the same. Yeah, because if you just, it is a uniform motion. If you shift it, it remains uniform but shifted. And this is the main property which allows for this interesting synchronization phenomena, so that the phase of oscillations is free. So you can shift it and nothing happens. It doesn't return back. There is no relaxation back in the phase. And this just represents, it is a representation of the symmetry of this dynamical system with respect to time shifts. Because if you have an autonomous system and you have a solution and you time shift it, it remains again a solution because there is no explicit time dependence. And this solution on the limit cycle is represented by the phase shifts. Yeah? So this will be the key property of this dynamics. Okay, Now, here it is all maybe illustrated in this way. So here above I showed several trajectories, so which all come to this limit cycle, but they are shifted in time and all shifted in the phase. And so the phase is free. You can imagine it as some position on the horizontal plate, where so this position can be arbitrarily shifted and there is no relaxation. And now, so after these two different dynamics of the amplitude and of the phase, it is clear so that if you have now external perturbations, the first candidate to be changed is exactly this phase because it is free. While the amplitude, if you perturb it, it will return back. So this is stable variable, so it will be maybe not so easy to perturb, but to perturb the phase is very easy because there is no any force of relaxation. And this lies in the base of the phase reduction approach, which I will now introduce. So essentially, so you see, so you start with maybe very complex dynamical system. There is a limit cycle. And then the idea is that any complex dynamical system, you can reduce just to one variable, which is essential. And this variable is the phase. So, and this is more or less independent on how complex is the system. It could be even some kind of partial differential equation or partial or differential delay equation. So it can be a very complex dynamical system, but nevertheless, there exists a reduction. There is mathematically, so there is a notion of Isochrons, which is not maybe well known, but it describes how this reduction is made. So I maybe introduce it here. You see, so the problem here is the following, that the phase is defined on the limit cycle in a unique way. Because you have a closed orbit, you can just parameterize it from 0 to 2 pi, and you can choose this parameterization in the way that rotation is uniform. It is simple. But you want also to do perturbation, so you need something which is the phase outside of this cycle. Now, the question is how to define the phase not on this orbit, but in some vicinity of it. And the idea is the following. You see, so there is a motion of some point on this orbit, and if we take some other point here, it will approach this limit cycle. And you can ask the question, so what exactly point on the limit cycle it will approach? So if, for example, you follow this point, and you see so that they come really to match another, so this is a situation when you can say, okay, I will attribute to this point the same phase as here. This is idea behind this isochron construction. And to be, maybe it is easy to comprehend in the following way. Let us observe this dynamics stroboscopically with the period t, which is exactly the period of this limit cycle, of this periodic motion. So what does it mean? So that we say, look at this point, and then after a period t, it will be exactly the same point. For this stroboscopic observation, each point on the limit cycle is a fixed point. Yeah, because you start point, after one period it will come back, it will be the same point, it remains the same point. So if you observe this point stroboscopically, it will be, all the points on the limit cycle will be fixed points. Yeah? It's the degenerate situation, but it is exactly because of arbitrariness of the phase. Now, if you now observe this point, also stroboscopically, it will come closer after one period to the limit cycle. It will be here, it will jump here, and then it will jump here, and it will converge to some point on the limit cycle. And if I start from another point, it will come here, it will come here, it will converge to some another point on the limit cycle. And I can draw a set of all points which converge to this one under stroboscopic map. So it will be something like this. It's a, so to say, stable manifold of this point on the limit cycle under stroboscopic map. And for this point, it will be this manifold, and it will be such a foliation of the neighborhood of this limit cycle. So this point, after one period, comes closer, closer, and converges to this. And this set of, you see, it is a uniquely defined set of manifolds, some kind of foliation, and it is uniquely defined. It is exactly how you extend the phase from the limit cycle to its neighborhood. Essentially, you can extend it to the whole basin of attraction. It might be that these lines will be not so smooth. Maybe they will here make many rotations, whatever. But for us, it's interesting, the neighborhood. Yeah? So this is this notion of isochrons, and with it, we not only have the phase on the limit cycle, but also in the neighborhood. Yeah? And now we can use this for construction of the perturbation theory. Okay, so here it is the same. It is written in a more, how to say, analytic way. You can use this foliation as a just change of variables, so that coordinate on here, it will be this coordinate A, and this will be the phase. Yeah? So that not only on the limit cycle itself, but also in its neighborhood, we have this equation for the phase and some equations for the amplitude of which is all other coordinates, say, transversal to the limit cycle. So this is what we achieve with the Isochrons. So we make this, how to say, parametrization, new parametrization. And now we are well equipped for the perturbation theory. Now we want to have, so it's just, okay, so what is chain rule of differentiation? And we have this. Now, this term is nothing else as a constant. It's just the definition of the phase, because the phase is defined in this way. So without any perturbation, it must be a constant omega naught. And so we get here, we have generally dependence on x, but we make some kind of perturbation theory. Because epsilon is a small parameter, in the first approximation, we assume that x is not very much different from the point on the limit cycle. Yeah, because we assume so that it will be, okay, perturbation of size, say, maybe epsilon. And epsilon is already here. So in the first approximation, we replace here x by x naught. Yeah? So we replace here x naught. And x naught is a coordinate on the limit cycle itself. And it is periodic. It is function of phi only. It is on the limit cycle, x is a function of the phase. Yeah? So we know this. And this leads to a closed equation where on the right-hand side we have a function of the omega t, because it is function here, and the function of the phase, because x naught is just unique function of the phase. And this completes this phase reduction. So from the equation, which was in arbitrary dimension, we get just one equation for the variable on the circle, which is of has this, and this you can explicitly calculate. So in many cases, this p is not a vector, it's just a scalar, because you just has one term in this forcing. So it is some, say, vector, constant vector multiplied with a scalar function of omega t. It is not the general case, but typical case. And then you can write this function like a product of this function of external of the time, so which gives you the form of the force with which you act, and multiplied with the function of phi, which is defined like this. And in this theory, it is called, this function is called phase response curve. So it says how your oscillator is sensitive to the external forcing of this type. So this is, but this is not maybe the most general case, so mostly general you have there. So you see, again, so now coming here, yeah. So it's already a simple situation because you reduced from very high dimensional system just to one one equation, non-autonomous equation for a variable on a circle. So it's already a great reduction. But in many cases, you can get inside with even more reduction. So if you use, again, a smallness of this parameter epsilon, and this is called averaging of the phase dynamics. So if one has this, say, suppose that omega is not very much different from this omega naught. So then, in general, on the right-hand side, you have slow terms and fast terms. And a good idea is to average over fast oscillations. So it is just some kind of what one would call maybe in other contexts adiabatic reduction, so that you say deviations of the phase will be slow compared to this frequency, and so on average you can neglect high frequency terms, and formally it is can be easily done if you write this function of two variables. It is 2 pi periodic in both of them as a double Fourier series, which will be the following form. And you keep only terms in this double Fourier series where m is equal to L, because only they are slow. And then you end with equation which is much simpler. So formally, you can also write this condition as some averaging of this function. And this will be a very simple equation where q is now not a function of two variables, but just function of one variable. It is a variable of this function of this difference, phi minus omega t. So you call this new variable the slow phase. It is essentially deviation between the phase of the oscillator and the phase of the external force, and then it will be extremely simple equation. is just a first order nonlinear origin differential equation. You cannot have something simpler, yeah? So it is a maximal simple equation. And analysis of this equation is very simple, so I may be, okay, so in a particular case, so this is generally a 2-pi periodic function. In the simplest case, where it is just a sine function, it is called Adler equation. Yeah? So Robert Adler was a physicist from Austria. He immigrated in the 30s to the United States, and there he worked in the electronic industry. Yeah? And it is interesting, so that he died maybe some 15 years ago, and there was obituaries also in German newspapers. Yeah, so I read a newspaper in Berlin, and there was an obituary of Robert Adler. And of course, not because this equation is so important. It may be important for us, but not for general public, but because he working at RCA company, Radio Corporation of America, he made one invention which is really we use every day. It is a remote control unit for TV sets. So it was his invention in some beginning of 50s. But he had a very good also theoretical background, so he derived this equation. It cannot be simpler, yeah? So, and the analysis of this equation is also very simple. So it just depends on the ratio between these two parameters. It has two parameters. One is detuning. It is where your frequency, driving frequency, is compared to the natural frequency, and the forcing strength. And if forcing is large enough, you have a stable fixed point in this equation. So that means that this psi will be a constant. And psi, I remind you, is the difference of two phases. So there is a constant phase difference between external force and your force. And this means also what people call also frequency entrainment. So the frequency of oscillator will be exactly that of the external force. Or it's called phase locking because this difference is a constant. And this is the synchronization phenomena for this periodically forced oscillator. Or you have a periodic orbit here if forcing is small or detuning is large, and this is asynchronous regime. Yeah? So, yeah? No, you see, yeah, of course. Yeah, yeah. No, it's, I would say, as far as I know, the first mathematical description was done by Appleton and van der Pol in beginning of 20s, but not with this equation. They used so-called weakly equation of quasi-harmonic amplitude, but there also, so essentially the first, how to say, description, not within phase reduction, but with two-dimensional equations was done by Appleton and van der Pol. And probably Adler more or less independently. But this is the simplest, so to say, way. It looks like I never had, so the first reference are really to Appleton and van der Pol. Birkhoff was probably not earlier than van der Pol. Appleton. Appleton, by the way, was rather prominent, so he got a Nobel Prize in '47 for, not for this, but for studies of atmosphere. He was in Cambridge, I suppose, and van der Pol was a postdoc with him in Cambridge, so they worked together, and then van der Pol returned to Holland and then continued more or less the studies. What? Sine? So you see, so you can put here any 2-pi periodic function. So suppose you have equation psi dot is delta omega plus epsilon. Now here it's any 2 pi periodic function. It can be like this. But nevertheless, so the point is that if you have this maximum and minimum, so if you have your delta omega is small, so then you have here a steady state. And if delta omega is large, constant, so it is above or below, you don't have a steady state. It holds, okay, here I wrote sine, but you can draw here any 2 pi periodic function. So it doesn't depend. So this may be a little bit quantitatively, but it's the same. Yeah? So just sine is the simplest one, but you can draw any 2 pi periodic function. Okay, so as a physicist, so if you look such equation, so people are inclined to draw a potential to think, okay, so it is not just ODE, but it describes some overdamped particle in some potential. And this potential has a linear part and periodic part. And two situations mean, so in one case you have minimum of this potential, and then you sit here, and this is synchronization, or in other case you don't have minima and you just slide down and particle moves. So it's just physical interpretation of this equation or the dynamics. So now you see, so this condition, if you put it on the plane which of parameters which are you use in the, say, experiment, and so here it is detuning, and here it is forcing amplitude, yeah? So then you see so that there is such a triangle shape which is called Arnold-Tong. It's exactly an example. So when so Arnold essentially has formulated his lemma that if something is named after a person, so then it means so that not this person invented it. And this applies also to Arnold lemma itself. And okay, but there is now tradition. So if you say Arnold-Tong, so this means synchronization region. Yeah. So here, okay, it is synchronization region. And if you cross it in this way, so for a forcing, and you draw here the difference of the frequencies, you see that the whole region, here it is, you have synchronization. Yeah? So it means so that you can perfectly synchronize in the whole region. Yeah? Okay. Now, I'll now give several examples, so how it is in everyday life. So these radio control clocks work in this way. So there is a signal from the station in Europe. So all is covered by this station, I suppose, in Frankfurt, and they get perfect signal, and all radio control clocks are then synchronized and are as precise as these atomic clocks standard. Although if you take these clocks away, some, I don't know, South America, they will still keep, so they are oscillators. They are not just like railway station clocks, which are, you need to force each motion of these clocks. So they will operate, but will be not so perfect. But in Europe, they are synchronized by this signal. Jet lag is another example of this synchronization by periodic forcing. So there is internal rhythm in, so people have the internal rhythm, and which is synchronized by the daylight so day-night so cycle of the Earth rotation. So when you move to America or to Japan, you have to resynchronize it, and this is your jet lag. So it's time to achieve a new phase of synchronization is exactly what is the period of jet lag. And so there are many things related to this. Now there is a full branch of medicine and physiology called chronobiology, where people investigate so how these internal rhythms, so how they are synchronized and how they're important. And you know that there are two types of persons, so early birds and owls, so those who wake up early and those who really maybe late in the morning. And this corresponds to whether your internal rhythm is shorter than 24 hours or larger than 24 hours. Your phase of synchronization depends on this. And okay, so there are also some practical things here. So this is example of this resynchronization. You see, so it's for astronauts in space. Because if they have some complex thing to accomplish in the mission in the open space, for example, they need to be in the good phase of their sleep-wake cycle. Yeah, so that they are really in a good attention and mood. And additionally, they should be in a proper phase because of the control station, which have to control them. And so you have to, they schedule this mission to some special hours, and they readjust rhythms of the astronauts so that the internal rhythm is resynchronized with the corresponding phase, so that they, at particular hours, they are mostly suitable for this. So there's a special program. Okay, so it's a conclusion to this elementary consideration of synchronization is so that there is this effect when the period of your self-sustained oscillator will be exactly the period of the external force. If you put a periodic forcing on your oscillator. Now, there is a more general framework because we made several simplifications in this theory. One of the mostly simplified was this averaging. So if you don't do this, so there is still one can do, and in the, so to say, in the beginning of all good books on the dynamical system theory, there is the theory of such systems of circle map. I'll briefly introduce it just to say so where there is some additional features compared to the simplified consideration. So the idea is that the phase reduction is the thing which is generally valid. So it's for more or less arbitrary system, you can still have a phase reduction. Why? There is because the amplitude is stable. So there is okay, so the theory which is called, as far as I remember, normal hyperbolicity, or maybe some other names are used in this dynamical theory, which says so that if you have attraction to some object, and in this case it is a limit cycle, then under a small perturbation, this object survives. Because if this attraction is strong enough. So you need relatively strong attraction, and then it means so that the object survives. And this object is, in fact, from the limit cycle, in the situation when you have time periodicity. I will now draw this limit cycle in this plane of x variables. and then there is a time periodicity, so time, and then there is this period of T external forcing, so that so this object from the limit cycle becomes a torus, because trajectory goes on this torus. And this torus is the object which survives because it is stable. So the phase reduction is in fact not a problem. So you can prove that for small forcing, there is a torus survives in the phase space. But now the issue which is not, so it's averaging of these dynamics on the torus. So generally, if you take this limit cycle at time 0 and at time which is the period of external force, so then trajectory essentially gives you a map from one point of this cross-section to another point on the limit cycle. And this is some kind of smooth map. The only thing you can say, so there is a smooth map, and all the theory is reduces to a generic, what is called circle map. So this is just what is exact. So Adler equation is not exact, but this reduction is exact. The only thing so that maybe in many cases it's difficult to obtain this function analytically, but you know that it exists and it is a smooth function. So this term is just phi, so this is a constant. If there is no forcing, it will be just rotation of the circle. And then the theory, all the theory, so of these circle maps, which is, say, one chapter in, if you look in book by, for example, Katok, Introduction to Dynamical Systems. So there is a chapter on circle map theory. Okay, you start from the case where there is no forcing, and then it is just shift of this on the circle. And you have to distinguish whether this quantity ratio of two frequencies is rational or irrational. Because in one case, you will have a periodic orbit if it is rational. And if it is irrational, so then this will be ergodic, how to say, motion on the torus. So it is irrational shift on the circle. Sorry, on the circle. Yeah. So this is without forcing. And then with forcing, you have to, what comes instead of this constant, you have, the good idea is to define so-called rotation number, the average number of rotations you make per one step. So this number exists in this limit. It is, doesn't depend on the initial point, because just two trajectories cannot differ by larger than 2 pi. And this quantity can be again be rational or irrational. Yeah. This, so if there is no forcing, you just have a shift on the circle. So this, because this is just a constant term. Yeah? You see this? It's just a shift. So you have a circle and you just shift a point by some quantity. Now, if this quantity is in rational relation to 2 pi, then you will come back at some point. If not, then you will continue to, it's just what is called in physics commensurate and incommensurate frequencies. But this is without forcing. Now, with forcing, because this term influences, you have to define this commensurate and commensurate in a more, how to say, sophisticated way. You just take a limit. So asymptotically, how many you? And this, again, can be rational or irrational. So if there is no forcing, it will be just the old number. But now it will be something. And then, okay, so, and this is, so this is what you physically observe, because this number exactly comes as an observation of the mean frequency of the oscillations. And then there is this dilemma, how to say, dichotomy. Rho, it is rational, say K over Q, and this means so that there is a stable periodic orbit. And this is irrational. And this means so that there is a quasi-periodic trajectory or quasi-periodic ergodic dynamics. So there is these two types of motion that are only possible. And this is called synchronization or synchronous motion. And this is called asynchronous. So, and what we studied previously, it was in the Adler equation. What this is described by Adler equation, it is just describes the only situation when P over Q is 1. So then this is described by Adler equation. And all others are missed because of this averaging procedure which was there. So you neglect them and you miss them, these other rational numbers. You keep only one the main one. All other are missed. But in reality, they do exist. And this is exactly what is missed by the Adler equation. And you have a more generalized picture of this Arnold-Tongs. And this is indeed so the picture which also Arnold studied in the beginning of 60s. So maybe this is the main resonance or main synchronization region, but there are another ones here, and there are. And in fact, from all, in principle, all rational synchronization region exists, but they are very tiny. And there is some kind of paradox of this. Okay. Yeah. Now, if you cross here, you don't see only one synchronization region, but several ones corresponding to different rationals. And this is what is called in this context Devil's staircase. You draw your observed frequency, and you see here it is the main region, and here it is some smaller regions. And in fact, so because there is a general infinite number of them, you have some fractal curve, which is describes general synchronization phenomenon. Okay, there is some paradox here, which, if I return back to here, so that only synchronization is stable because it corresponds to stable periodic orbit, and quasi-periodic motion with any perturbation in any vicinity of it, there is a synchronization region. So one looks stable and another looks unstable, yeah, because with any perturbation you miss it. But if you consider this not from the viewpoint of some stability, but of the viewpoint of, how to say, probability to observe, it will be a contrary situation. So probability of a quasi-periodic motion is large, and this is analogous of KAM theorem, Kolmogorov-Arnold-Moses theorem in the Hamiltonian dynamics. So that, in fact, here for small forcing, quasi-periodic motions prevail, although they are not stable. And this is also, so this is, okay. I'll maybe, so in some cases you can get this curve analytically. I maybe skip this. You see this circle map, yeah? So it's, you know that it exists, but it's not so easy to find it because you need to solve nonlinear equation here on this way. But even for experimental situations, people do this. And for example, you can do the following. You see here, it is a neuron, firing neuron is depicted. And you can just experimentally put a pulse of it and look what is happening with this period. And this gives you a corresponding map. So if you now will make this force periodic, so you will know how this period depends on the previous period and on this forcing. Yeah? So in many cases, you even can this to obtain this mathematical object not by solving differential equations, but just from the experiment. And for example, here, so this is experiment how, or okay, so this is something like map, but it's how we respond to the small pulse of high illumination in changing our daylight cycle. So there are periods where we are not so sensitive, and then so here bright light will advance our circadian cycle, and here it will delay it. Yeah, so this is, you can do with humans, with other animals, these experiments. And for example, there is a famous picture of synchronization of Josephson junction, where these regions, devil staircase, to some extent is observed. These are called Shapiro steps. There were in the 60s these experiments of putting periodic radiation on the Josephson junction, and they observed at least several steps, which in the theory there is infinite number of them, but of course very small steps you cannot observe experimentally. Now there is, you see, so it is exact theory, but it is of course restricted to small forcing, because all these ideas of normal hyperbolicity, they are based on the fact so that you are close to a stable situation, but you can be go further. And for example, if you formally write a map, you can come to the region where it is non-invertible circle map. You cannot obtain this non-invertible circle map just from from such simple dynamical systems, but nevertheless, so it gives some properties which also are observed in reality for strong forcing. So here, for example, overlap of the Arnold tongues. So you can have several synchronization patterns simultaneously, which means multi-stability. So depending on initial conditions, you can have one synchronization pattern, for example, 3 to 4, and from other initial conditions, you have synchronization pattern 3 to 5. You can even have chaos. I'll maybe go to this picture, which more or less shows that, so you see, so here in the middle is this stable torus, so it's cross-section. And this is ergodic situation, and this is situation when you have stable point and unstable point on this torus. But you see, so the for large forcing, it can be that this torus becomes destroyed. For example, so this stable point on the torus will be not node anymore, but a focus. And this means, so you see, so this smooth torus doesn't exist because, so it is a now spiral, and here different situations can happen. Or there are other ways how a smooth curve, invariant curve can be folded through some homoclinic bifurcation. So this is really a subject of studies in bifurcation theory, and I am not sure that all these scenarios are well studied. So this is some complex dynamics at strong forcing. Now I will now try, okay, so this is conclusion to this part. So exact theory describes exact model for small and moderate nonlinearities. It's M to N locking, so Arnold tongs, and gives some hints so that probably could be some kind of transition of chaos also behind it. Averaging. Now, you see, in the averaging, you keep only this possibility, and you throw out all other possibilities of the, yeah? So in averaging, you see, so there is a, so to say, you look on the main resonance, and all trajectories which are, how to say, not belong to the main resonance, you essentially, okay, not with straight lines, but you neglect, so to say, curvature of them, small curvatures of them. So you think, okay, they are more or less straight lines. And this throws away all other possibilities of other resonances. You just throw them away together with the averaging. If you do this average, or if you go to higher and higher orders, then you keep this curvature, and then you can resolve more and more resonances. So you can say, okay, so Adler is a first order thing, but if you go to higher orders, so you, in principle, can get more and more resonances, and there will be formally infinite number of them, all rationals will be there, but maybe very tiny if you could, okay, but they, okay, you can prove that they are there, but to obtain them analytically, you need really to go to very high order approximation. So this is how this relation, exact circle map and average circle map, how they are related to each other. Okay, now, I will try, okay. So situation of two oscillators are nearly the same. You just have, instead of one phase and one, so to say, external periodicity, you have now two phases. So that it means so that they are just, you start with two such equations, and through perturbation theory, you just get two such terms. Formally speaking, so it is almost the same situation as with periodic forcing. The only, so it's by averaging you get the same Adler equation. The only difference is that now you can indeed or physically distinguish the cases of positive and negative this parameter epsilon. If depending on the sign of epsilon, either delta phi 0 or pi will be stable. And this is called in-phase and out-of-phase synchronization. So the two oscillators can be synchronized in phase or out of phase if they look like this. this is, if you compare this to statistical mechanics, it will be ferromagnetic coupling and antiferromagnetic coupling when two spins have different orientations. Now here there is some series of examples starting from Huygens, who observed this first in 17th century, and then Lord Rayleigh. And these are, so this is Appleton and this is Van der Pol, who really observed this in 20s. And this is this experiment by Appleton. He had two electronic generators, and he observed this synchronization region experimentally. And you see, so this difference of frequency here, cannot be negative because he measured this bit frequency just with airfoils. Yeah, so this is a device to measure the frequency difference. Okay, with metronomes, I will skip this with Josephson junctions. So essentially, two oscillators is the same picture. The only difference is, and it will be important if you have many of them, they can be in phase and can be out of phase. Yeah? Can be also phase shift, but typical cases are these. More typical are, okay, it could be in principle any. But if you have some kind of symmetry, so then it is typically it is just epsilon. But in general, so in general it could be any. It just depends on this function. So how this function looks like. How this function. So it is in many cases it is just a sine function. So it means so that it is a 0 or pi, they are stable or unstable. Okay, now you see, so this, so we have here not just non-equilibrium systems, but we have stochastic dynamics there. And so at the end of this lecture, I want to represent so how you can generalize this picture to stochastic and chaotic systems. Now, probably the most elementary thing is the following. So you just start with the phase amplitude equations, and you just add some noisy term like people do. So you write something like Langevin equation, or you say your clocks are subject to some external fluctuations. Maybe for biological system, it is quite natural so to be in some noisy environment. And you model this, you just take, instead of differential equations, you write stochastic differential equations. And moreover, you are not restricted to considering here maybe something like white noise or Gaussian white noise. It could be any fluctuating term or any noise. And then the same idea of phase reduction can be done because here you have stability in the amplitude, and you want to exclude this amplitude from the equation and write an effective equation in some approximation just for the phase alone. And people did this in some examples. Got some formulas so that you have effective equation. So essentially, you have effective equation for the phase, and it means so that you can now proceed and you write equation something like this. So this is equation without any random inference. What we discussed, so it is some particle in the minimum and particle sliding, and now you put noise at top of it. And it is clear what will happen here just from the very qualitative consideration. If you have particles sitting in such minimum and you put noise on it, drive it, then it can overcome this barrier and go down. if the fluctuation is large. So it can be often or seldom, yeah, depending on how strong is your noise and how high is this barrier. But if you say have Gaussian noise, you would not expect that this particle will sit here forever. It may happen only if you have bounded maybe noise. But if you have some large fluctuations, or even seldom, so you will sleep. And this means so that noise makes synchronization not perfect. So you are not exactly here. You maybe from time to time you slide. And this means so that you will not have exactly the same frequencies, but maybe very small. OK, so it will be some deviations from this. So practically, if you just look on numerics, maybe, so if noise is small, you see so that there are phase sleeps, which are quite seldom. You have long synchronization periods. And if noise is stronger, so you will get quite often this sliding. So noise destroys synchrony. So this is essential message. Now, let me also return back to one thing which was I discussed in the beginning. So we defined isochrons and the phase for deterministic oscillators, and it was a perfect, good definition. The question is, can we do the same for noisy systems? It is not, I don't know any, how to say, exact mathematical theory, but as a physicist, one can think in the following way. So maybe I'll put here again this picture. So it was a limit cycle, and for each trajectory, we can go around and more or less fix what happens after one period and such thing. Now, if now these trajectories are noisy, still it can happen that they go around. So we still observe oscillations, but maybe not in such perfect way. Now, what would be, and then we somehow return back, but we never converge here, so you continue moving around in some noisy way. Now, but still, so we can do some kind of foliation so that you have some, how to say, manifolds, and you go around and you come from here. Maybe you even several times cross it, but more or less you come back here after one round. It means that still with noise, you do observe, how to say, oscillations. So it's not completely noise, but it's still you have oscillations. Now, so now what is coming on the instead of, how to say, period. So now we have, I would say, so mean return time. So you can start look on all noisy trajectories which come from this line, and you can define a mean return time coming back to the same manifold. Yeah? So this mean return time will be something like average period. And you can define these lines, say on these two-dimensional projectors, as the lines when the mean return time is a constant. So that mean return time starting from here, from here, from here, from here, from here, it will be all the same and equal to the mean first return time. And this generalizes the notion of isochrons, because if there is no noise, it is exactly the same notion as without it. But with noise, it will be generalization. And it's interesting that you can define this even for systems where you don't have without noise oscillations. So for example, suppose that without noise system will be sit here, and it is so-called excitable system, but noise drives it from this point here, and it makes oscillation, comes here, drives again. So it can happen that without noise you don't have oscillations, but with noise do have them. So you still could have something like Isochrons and good definition of phase for noisy systems in this way. Okay, now I come to chaotic oscillations. Now, chaos is a general phenomenon in nonlinear dynamical systems, and chaotic oscillations are, of course, not periodic. So it is what is called deterministic chaos. They have instability, they have Lyapunov exponents, and at least one of them is positive. But if the system is autonomous, it has exactly 1, 0 Lyapunov exponent, because it still has invariance toward the phase shifts, toward the time shifts. And if you look on such a chaotic oscillator, you can say, so why not to defining phase just this angle? Yeah. So indeed, you could do this. You can define it as through Poincaré map or in some other way. And even now you can say, okay, what about Isochrons? Now it is a problem because the return times now are deterministic and they are all different. And you cannot make a unique return time back because they're simply different periods or different return times. You can more or less make them not a constant but uniform, and this will be a good definition of the phase for such a chaotic oscillator. But the return times are not exact, and this means so that we have a situation with effective noise. So you have still, you cannot have this because, yeah, and then, so you have still some term which depends on the amplitude. If you neglect it, or you can consider it as effective noise, and then the situation will be very close to situation with noise. You don't have maybe perfect synchrony, but synchronization of chaotic oscillators will be like those of noisy ones. So practically, you do observe, in many cases, a good Arnold tongue, except maybe for small forcing. And so this is generalization of synchronization to chaotic systems. You can pace it, so it still remains chaotic, but now its frequency of rotation is exactly that of the external forcing. So, and this is probably my last slide. So, if you have periodic oscillators, you can synchronize them by external forcing. Also, two systems can synchronize each other to some common frequency. If you have noisy situations, it will be not perfect, but definitely for small noise, you still observe this effect. And for chaotic system, if they are good enough, so if they really look like a rotation around something, you can also observe this effect, so that the frequency will be exactly or almost exactly locked by the external forcing. Okay, so this is probably the end of my first lecture. Yeah, if there are questions. So my plan is so that I will also speak more stochastic effects, so-called synchronization by common noise, and then also about many systems. There are very interesting phenomena which link this to some problems of statistical mechanics, especially mean field approximation there, which many of them are still very, how to say, hot topic of current research. We'll see. Okay, so we meet at 2, yes? Okay.